Hello, my name is Darren Thomas and I'm the Director of Educational Research Techniques. In this video, we're going to take a look at the periodic function cosecant, and take a look at its properties and behaviors. So let's go ahead and get started. So you can see here at the top, we have the equation for it. This is just like the equation for the other periodic functions and for the sinusoidal function, but the difference here is this guy right here, the CSE, which is short for cosecant. And so, of course, you know the A is like the stretch factor. We've talked about that before. There's no amplitude with most of the periodic functions. The B term is for determining the amplitude. We've talked about that as well. And to get the amplitude, you do 2 pi over the absolute value of B, whatever that is. C is kind of your phase shift, moving it to the left or to the right. And of course, D is kind of your vertical movement, where the moving it up and down. So, in case you don't know, as a quick review, the cosecant is basically the reciprocal of the sine function. So for the sine function, it's basically opposite over hypotenuse, and again, we're referring to a triangle here. So if I'm trying to figure out this angle right here, the opposite is over here, obviously. The hypotenuse is here, and this will be the adjacent, if you will. And so the secant is just hypotenuse over opposite side. That's the difference. And so you're able to use this for other purposes when you're doing trigonometry things. All right. So here's a picture of when you graph the actual cosecant, if you will. And you can see that it's periodic because you have these asymptotes, if you will. And this is where when the denominator is a 0 and you can't divide, so it disappears for a while and then it reappears. Kind of like the blinking of an eye. You blink and then it's back. You close your eyes, it's gone, but then you blink, you open your eyes again, it's back. Something like that, periodically like that. And so it's called periodic because this interval is always consistent between the various waves here. And so that's kind of what's happening right there. Now, if you're really, really curious, the asymptotes can be calculated by using x equals c over b plus pi over the absolute value of b times the quantity of k, if you will. And so that's how you do that. But like I said, again, this is the basic cosecant where there's no manipulation of the a, b, c, or d term. They're all basically set to either 0 or 1, if you will. And that's how it behaves. Let's move to the next one. Now here, the black line still represents our regular cosecant, but now we're manipulating the stretch factor, or the A term, often called the amplitude when you're doing a sinusoidal function. Now, here in this example, you can see that when A is greater than 1, things kind of get compressed a little bit. So if you look at the blue line, compared to the black line, it's compressed. It's moved up a little bit, and it's more pushed together. Now, when the A term is less than 1, as you can see here, and what I mean by less than 1, I mean like absolute value of 1. When it's less than 1, you can see, when it's a fraction, if you will, you can see how it's kind of stretched out a little bit. And so you can see with that, it's more pulled apart. The distance here, is greater now compared to right here or right here. And so that's kind of what's happening. Well, let's go to the next one now. Okay, now in this particular example, we're now manipulating the B term. And so again, the black line represents the regular one, and you can see here with the when the B term has the absolute value that is greater than 1, you can see that things get compressed. In other words, there's more waves. The period is shorter, smaller, more pushed together. You can see that there is more. And of course, when the absolute value of the B is less than 1, you can see how things are spread out here, way more spread out. In other words, now it takes two black waves here to make one red wave when you have less than 1. But when it's greater than 1, you can see it's now there's 3 of them when it used to be only 2. You can see how it gets crazy. All right, here's the last one. Now, with the green line, again, the black line is our regular line. With the green line, we're manipulating the C term, so that moves things to the left or to the right. It's called the phase shift. And so you can see here that if you put a -1 in there, it moves to the right 1. And of course, now the yellow term below it is where we're manipulating the D term, and that moves things up or down. So you can see that when we add 1 to it, you can see that it goes up one unit vertically on the y-axis, if you will. And of course, if we were to take away, it would go down 1 unit. And so that's kind of the behavior that it's taking on at that particular moment. So let me kind of go back and recap what's happening here and then wrap up the video. So in this video, we took a look at the cosecant function and how it behaves. It has all the same terms as the other periodic functions, the a, b, c, and d term, and they all have the same behavior. We're just looking at things from a slightly different perspective in terms of what ratios we're dealing with. And so cosecant is where you have is the reciprocal of the sine function, where you have now instead of opposite over hypotenuse, you have hypotenuse over opposite. That's kind of the main difference. And then the behavior of the actual function is, like the other periodic functions, nothing amazing or spectacular to talk about there. But it's good to review these things, especially if you're new to these ideas that we're talking about. So I hope this video was useful for you and you were able to understand what we were talking about. My name is Darren Thomas. I am the Director of Educational Research Techniques. Take care.